In this video, we're going to look at the 4 principles of experimental design. So at this point, you should pause the video and read through the 4 principles. The first being control, the second being randomize, the third being replicate, and then we also have blocking. So let's say we're planning an experiment to see whether the new pet food is safe for dogs to eat. We'll feed some animals with the new food and the others a food known to be safe, comparing their health after a period of time. In this experiment, how will you implement the principles of control, randomization, and replication? So what we can do, since we're feeding the animals some of the new food and then some of the food that we know is safe, we would want to make sure that we control the portion sizes eaten by the dogs, right? To reduce possible variability, maybe, you might want to house the dogs in similar environments to ensure that each got the same amount of water. You'd want to think about exercise, play, sleep time. Those are all variables that can affect the outcome once we measure. So we would want to be really careful with that. Okay, so as far as the control, we'd want to control portion sizes. And then we would also want to reduce possible variability. And some sources of possible variability could be, you'd want the dogs to be in similar environments. You'd want to maybe ensure that they got the same amount of water. Should be H2O. Exercise, play, etc. Those are all things you would want to try to control. As far as randomize goes, right, we would want to randomly assign the dogs to the 2 treatments. And again, the treatments would be the old food and the food that we know is safe. And then as far as replication goes, we would want to replicate by assigning more than 1 dog to each treatment, right? We don't want just 1 dog in a treatment group because that's really not going to tell us much. We need to be able to compare. We could also replicate by repeating the same experiment. So, or, if you had funding, if you were working for an organization, if they give you funding, you could replicate the entire experiment. An experiment is carried out over time with specific actions occurring in a specified order. Sometimes it's helpful to look at a diagram, which is just a procedure that helps you think in terms of experiments. Okay, if you could please pause your video. And before you pause, let's take a look at that diagram related back to the pet food problem. So you've got your random allocation and we're looking at dogs, right? So we would want dogs in both groups, okay, by replicating that way. And we would randomly assign dogs to each of the 2 treatment groups. Maybe these groups will get the new, and then these groups will get the safe, the food that we know is safe, and then we would compare at the end, okay? And that would be done through a veterinarian assessing, maybe through blood results or, whichever other ways that they assess. Okay, now you can pause the video. And for this problem, you're going to tell me the factors, the levels, how you're going to completely design this randomized experiment using those principles. You don't have to worry about blocking. That's not always a requirement for a good experiment, but we'll talk about blocking and when it's good to use it. An ad for Optigrow plant fertilizer claims that with this product you will grow juicier, tastier tomatoes. You'd like to test this claim and also wonder whether you might be able to get by with half the specified dose. How can you design an experiment to test Optigrow fertilizer? For your experiment, use a completely randomized design in one factor. Here we're going to think, show, and tell. So let's talk about, first of all, what is the factor? The factor here is the fertilizer. Okay, and we have 3 levels. And the levels that I would want to use here are some plants with no fertilizer, some with half, and also some with the full dose. Okay, and we would need to randomly assign plants to those treatments. Let's say we're going to get, I don't know, we'll do an even number here. Since we have 3 treatment groups, let's do 24 because 3 divides into 24. Now, you don't need to have the same number of plants per group, but I just like it to work out like that. Okay, and you basically can come up with your own. So we're going to obtain 24 plants, right, tomato plants, of the same variety. Again, we would want to do that to control for any variability. And I meant to say variety here. So I guess to do that, we would want to buy it from the same garden store, right? So obtain 24 plants of the same variety from same garden store. Okay, since we have 3 treatment groups, we would maybe do 8 plants in each treatment group. Okay, and we would have like plants in equally sized plots. We would want to reduce variability, so again, control. So we would want to make sure that they all had equal amounts of sunlight, rain, temperatures. You know, you want to make sure like maybe like there's certain plots that aren't in the shade of a tree while the other ones have full sunlight. All of those things can affect the response. So 8 plants in each treatment group, and we could say something like equal sized plots, similar amounts of water, sun, temps, etc. And what we would do is we would randomly assign the plants into the 3 groups. Okay, and we talked about in chapter 11 ways you could do that. You could number the plants maybe from number from 00 to 23. And we can just, use a random number table or look at 2 digits in the random number table as we go across the row. And the first, every 2-digit number that comes out that's between 00 to 23 will be assigned to the treatment group. So you could do like the first 8 will go to the no fertilizer group, and the second 8 will go to half, and then the last 8 can go to the full dose. Okay, something like that. So use a random number generator, like Google has one, or just a table. Okay, looking again at 2 digits at a time, and the first 8 will go to the first treatment group. So they get no fertilizer. The next 8 go to half, and then the last 8 go to the full fertilizer. Okay, and of course we would grow the plants until the tomatoes are mature. We would want to set up maybe a scale of juiciness and tastiness and have judges. Several people you would want to taste the tomatoes and rate them, right? So we can have judges rate tastiness and juiciness using a scale. Okay, once the plants are matured. And if you're a visual person, this is where the design would help. So if I add in an extra page here, I'll draw the design for you. So what I'm thinking is, so here's your design. You've got your 24 tomato plants, okay, from the same store, of course. We've got our 3 groups, and you're going to randomly assign the treatments to the 24 plants. Okay, you've got group 1, which we said was treatment 1. They're not getting any fertilizer, so we call that the control group. And then group 2, they're going to get half the dose. So this is treatment 1, 2. They get half the dose of fertilizer. And then our last group, group 3, they're getting the full fertilizer. And we would have 8 in each group. And then at the end, we're just going to compare the juiciness and tastiness. And that's how we would measure our variable. We said we're going to use judges. They're going to use a scale. And one thing to keep in mind is if the differences in the taste and the juiciness among the groups are greater than I would expect, I might be able to conclude that those differences can be attributed to the treatment with the fertilizer. So if those differences among the treatment groups are big enough, we'll attribute the differences to the actual treatments, in that case the fertilizer. How can we decide whether the differences are big enough? The real question is whether the differences we observed are about as big as we might get just from the randomization alone, or whether they're bigger than that. If we decide that they're bigger, we'll attribute the differences to the treatments. In this case, we say the differences are statistically significant. Okay, and significant doesn't mean like as important. So think of it like this. An outcome is statistically significant if the probability that it happened just by chance is so low that we're convinced there must be another explanation. So in our OptiGrow example, a good way to look at this is to look at how the results vary among the plants that get the same treatment. For example, so let's pretend that we have our OptiGrow problem here. For example, in the 2 pairs of box plots, the centers differ by exactly the same amount. Okay, so here's your center, your medians, right, for both. So they differ by about the same amount. In the pair on the left, though, the difference appears to be larger than we'd expect by chance. And the reason is because the variation is quite small within the treatment groups. And I can see that because the box plots are smaller than the two on the right. So the larger the difference between the groups is unlikely to be just from randomization. In the pair on the right, the same difference between the centers looks less impressive, but there's more variability there, right? So there, the variation within each group swamps the difference between the two medians. We'd say the difference is statistically significant in the pair at the left and not statistically significant in the pair at the right. Okay, let's kind of review what we've been talking about here. There's been a lot of vocabulary and in terms of the experimental design problems. So if you could pause the video and answer those questions there, and we'll go over it. At one time, a method called gastric freezing was used to treat people with peptic ulcers. An inflatable bladder was inserted down the esophagus and into the stomach, pardon me, and then a cold liquid was pumped into the bladder. Now you can find the following notice on the internet site of a major insurance company. Our company does not cover gastric freezing for chronic peptic ulcer disease. Gastric freezing for chronic peptic ulcer disease is a non-surgical treatment which was popular about 20 years ago but is now seldom performed. It has been abandoned due to a high complication rate, only temporary improvement experienced by patients, and a lack of effectiveness when tested by double-blind controlled clinical trials. What did that controlled clinical trial experiment probably look like? So in letter A, we are asked what is the factor in this experiment? And the factor is the type of treatment for the peptic ulcer. What was the response variable? Remember, that needs to be measurable. So they're, if you think about it, they would be measuring the relief from the gastric ulcer pain, probably based off of the evaluation of like a physician, right? What were the treatments? So the treatments here are the gastric freezing and some alternative control treatment. How did researchers decide which subjects received which treatment? Well, remember, the treatment should be assigned randomly. Were the results statistically significant? No, the website reports that lack of effectiveness, and that indicates no large differences in the patient's healing were noticed, right? So if there's not a lot of large differences, then no, the results were not statistically significant, as in the box plots we looked at, where there was larger variability. There really was a lack of effectiveness or a lack of difference. So no. Okay, we'll stop the video there. In the next video, we're going to look at making sure that experiments, are representative of the population, and we'll look at blinding, and we'll look at placebo effects.